Hi, my name is Don Stull. I'm a postdoctoral fellow in the computer science department at Northwestern University. In today's lecture, I will be discussing Kolmogorov complexity. I'm particularly excited about this because I use Kolmogorov complexity in my own work to study objects and sets of mathematical analysis. Okay, to begin with, to motivate this lecture, I want to pose the following philosophical problem. What does it mean for an object to be random? And for concreteness, let's make it concrete. So for concreteness, let's focus on binary strings. So what does it mean for a finite binary string to be random? So at first glance, it's not even clear that this question type checks. We typically think of randomness as a process, shuffling a deck of cards or pulling random balls from a hat or something. But I'm asking, what is the intrinsic randomness of a finite binary string? So while it might initially seem confusing, it does seem like humans have an intuition about this question. So consider the string of all zeros, or the string 0, 1, 0, 1 repeating. These strings somehow don't feel random. Okay? These things don't feel random. Even though we haven't really defined what random is. Any reasonable definition of randomness can't describe these strings. There's too many patterns involved with these strings. And so that really, if you think about this a little bit more, you might come to the conclusion that any string with some sort of exploitable pattern can't be random. The key property that these strings have patterns. And so any string with a pattern doesn't seem like it would be random. Or equivalently, because if a string has a pattern, then it can be compressed by just describing that pattern. Random strings shouldn't be compressible. But this poses another question, which is, what's compressing these strings? What do we mean by compressible? What's doing the compressing? So in the early or middle 1950s, Kolmogorov, Solomonov, and Chaitin independently answered this question by using Turing's newfangled machines. So So Kolmogorov, Chaitin, and Solomonov used Turing machines to study how random a finite binary string is. And this is the definition they came up with. Let M be a Turing machine, and let X be a finite binary string. The Kolmogorov complexity of X with respect to M which is denoted C sub M of X, is the minimum length program which causes M so the minimum length program which causes M to eventually halt and output X. Okay. If no binary string causes M to halt and output X, then by convention, we say that the Kolmogorov complexity of X with respect to that machine is infinity. Okay. So in the following lectures, we're going to be exploring this definition, and we're going to be in particular aiming for the following fundamental results of the field. So I'm going to call these the 3 pillars of Kolmogorov complexity. Let's see. So these fundamental results are as follows. The first are the existence of optimal machines. So these are machines which essentially minimize the complexity. Okay. These are the strings which give the lowest value for every string intuitively. The second pillar, the second fundamental result that we will prove in this video are that most strings are random. And finally, we're going to show that the Kolmogorov complexity function is undecidable. In fact, it's really undecidable. It has a lot of interesting computability properties, most of which we won't explore, but that is one of the important properties of this field, that the complexity function is highly non-computable.